In this lesson, we'll understand why keyword search often fails and how embeddings plus vector databases make semantic search actually useful. We'll go step by step, and after a few sections, I'll test your understanding with quick quizzes. Let's start with the core problem. In traditional keyword search, the system looks for matching words, not matching meaning. So a query like "can't log in" may completely miss a document called Authentication Troubleshooting Guide. Technically, the system is working, but practically it is not helping the user. Semantic search changes this by matching intent and meaning, not just tokens. An embedding is a numerical representation of text. You can think of it like converting a sentence into a point in a very high-dimensional space. If two pieces of text mean similar things, their vectors land close to each other. If they are unrelated, they stay far apart. This is why embeddings are so powerful for retrieval, recommendation, and RAG systems. Here is one important practical point. Every retrieval pipeline depends heavily on embedding quality. If the embedding model does not place relevant chunks near the query, the wrong context gets retrieved. And once poor context enters the prompt, even a strong LLM cannot fully rescue the answer. So better retrieval starts with better embeddings. Now let us look at this in a simple table format. Vector database options. Common choices for semantic search systems. Now let's look at the main infrastructure choices. Pinecone is popular when you want a managed service and less operational burden. Weaviate is strong when you need richer querying and flexible self-hosting. Chroma is great for local development and fast prototyping. Fairface is not a full database, but it is extremely powerful for high-performance similarity search inside custom systems. Not all embedding models are equal. Some are strong for general English retrieval, some for multilingual use, and some are better when you want self-hosting or privacy. Benchmark leaderboards like MTEB are useful, but the real test is your own domain data. In production, domain-specific evaluation matters more than shiny benchmark numbers. Now that we've covered embeddings basics, let's test what we've learned so far.
Here's quiz number 1. See if you can get it right.
Question 1. Why did the keyword search system fail in the article example? The correct answer is, it required exact word overlap. Keyword search depends on token matching, so "can't log in" did not match Authentication Troubleshooting Guide, even though the meaning was similar. Question 2. What is an embedding? The correct answer is a list of floating point values representing meaning. Embeddings convert text into numerical vectors that capture semantic relationships. Question 3. Why is embedding quality important in RAG? The correct answer is, it determines whether relevant context is retrieved. If retrieval is poor, the LLM receives irrelevant context, which reduces answer quality. Once text is converted into vectors, retrieval becomes a nearest neighbor problem. The query is embedded, then the system finds stored vectors that are closest to it. But closeness depends on the metric you use. That metric affects both relevance and speed, so it is not just a mathematical detail, it is a product decision too. For most text search applications, cosine similarity is the safest default because it focuses on direction, not vector magnitude. Euclidean distance, or L2, can be distorted by vector length unless you normalize carefully. Dot product can be very efficient, especially when vectors are pre-normalized and many systems use it internally for performance. Choosing a vector database depends on your constraints. If you want zero infrastructure headache, managed services are attractive. If you need more control, self-hosted options can fit better. And if performance is absolutely critical, teams often use FAISS in the inner search loop, while metadata and service layers are handled separately. Now that we've covered similarity and storage, let's test what we've learned so far.
Here's quiz number 2. See if you can get it right.
Question 1. Which similarity metric is usually the default for text embeddings? The correct answer is cosine similarity. Cosine similarity is commonly used because it compares semantic direction while reducing the effect of magnitude. Question 2. Which option is best suited for local prototyping according to the article? The correct answer is Chroma. Chroma is described as lightweight and useful for prototyping and local development. Question 3. What is FAISS mainly known for? The correct answer is High Performance Similarity Search. FAISS is widely used for fast similarity search, often inside larger custom retrieval systems. If you compare every query vector against every stored vector, you get accurate results, but it becomes too slow at scale. That is why approximate nearest neighbor indexing is used. ANN methods trade a little recall for a huge gain in speed. The key lesson here is simple. There is no universal best index. You must benchmark based on your data, recall target, and latency budget. Long documents cannot be embedded as one giant block, so we split them into chunks. A practical sweet spot is often 256 to 512 tokens. If chunks are too short, they lose context. If they are too long, the semantic signal becomes diluted. Overlap is important because facts often sit near boundaries. And metadata like source, section, and page number is essential for filtering, citation, and debugging. General-purpose embedding models are good, but specialized domains like finance, legal, or medical language often need more. Fine-tuning helps the model learn that two different phrases may mean the same thing inside a domain. Usually this is done with contrastive learning, where similar pairs are pulled together and dissimilar pairs are pushed apart. Interestingly, a few hundred to a couple of thousand good pairs can already make a real difference. Dense retrieval is excellent for semantic meaning, but it may miss exact terms like product codes or error IDs. Sparse retrieval, using methods like BM25, is excellent for exact keyword matches, but weak on paraphrases. Hybrid search combines both. And because dense and sparse scores are on different scales, production systems often use reciprocal rank fusion, or RRF, which merges results based on rank positions rather than raw scores. Now that we've covered production retrieval, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. Why is ANN indexing used? The correct answer is to trade a little accuracy for much better speed. Approximate nearest neighbor methods reduce search time dramatically while keeping recall reasonably high. Question 2. What is a practical chunking guideline from the article? The correct answer is use overlap between consecutive chunks. Overlap helps preserve information that might otherwise be lost at chunk boundaries. Question 3. Why is hybrid search useful? The correct answer is it combines a semantic and keyword retrieval. Hybrid search captures both meaning-based matches and exact keyword matches, giving stronger retrieval overall. That's the foundation of semantic search. If you understood these building blocks, you're already thinking like someone designing real-world RAG systems. In the next lesson, you can go deeper into implementation patterns and performance tuning.